Hello, I am Mohammad Asif Iqbal. I am going to demonstrate a 4-bit computer using Verilog. The general architecture of the computer is as follows. The program counter here counts in the increment of 2 and is connected to the main bus. There is a memory address register which takes the value of the program counter, and the address is fed to the RAM, which is a 16-byte RAM. The RAM is again connected to the bus. There is again an instruction register which sends the instruction to controller sequence. The controller sequencer then produces a control word which controls the other parts of the PC. There is an accumulator which is a register and another register which is B register, both of which are connected to the arithmetic and logic unit. Here the arithmetic and logic operations are conducted, and the output is connected to the main bus, and there is also an output register which displays the output. There are some additional parts for implementing some other functions like stack. Stack is like a 16-byte RAM, but it performs slightly differently from the main. There is a stack pointer which points at a specific position of stack. Stack pointer points to the position where we can read or write a data in the stack. There is also a temporary register connected to the bus. We will use this register to exchange the value between A register and B register. There are also two flag flip-flops. The first is carry flag, which indicates the carry coming from adder or subtractor module. And there is another input which is rotate in. It is actually connected to the accumulator. The rotate out is again connected to the accumulator. These two lines are used to rotate the contents of the accumulator with the carry. There is also a zero flag which indicates if the contents of the accumulator are zero or not. It takes value from arithmetic logic unit and outputs the value in program counter. Because if we want to implement the jump if not zero command, then we will have to use this value in the program counter, update the current line of the program. Now we will demonstrate the procedure of the PC using some example programs. In this first program, we write move a address, which copies the content of address 1, which has 3, to A register. Then we exchange the value BA. So now B has 3. Then we again move A address 2. Address 2 has 12. Now if we add AB, so now the result of the addition will be stored in A, which is 50. And then out A, which moves the value of A to out register. Halt stops the clock, so the program is stopped. Now if we look at the simulation results, firstly we have loaded 3 in the accumulator, then we have done the exchange command. So now B has 3 and A has 0. Now we again load 12 to the accumulator here, and then we add AB. So now A scores 15. Here we can see that accumulator has 15. We output the value of A. Here we can see the output register has the value A. And then when the halt occurs, the main clock stops, so the computer stops running the program. In the second program, we have done the same thing, but we have used subtraction instead of addition. So the value is 9. We can see that the output value is 9. In this program, we have done the increment operation. In this first line, we have written move a byte. The value of the byte is this, and it loads the byte into A. Then we increment A, which adds 1 to the value of A, and then we output which is this. So we can see that the simulation results matches with our program. In this program, we first move the byte, which is all ones, into A, then increment A, Here the result will be a equal to 0 and carry flag will be equal to 1, because if we add 1 to this, all of the contents of a will be 0 and carry flag will be 1. And then if we rotate with carry right a, then it will do rotate with carry the contents of a. Then if we output a, then we will have the value this. So here in the simulation we have we can see the same thing. First we load all ones into the accumulator, then we increment the value of a, which makes accumulator 0 and the carry flag 1. Now if we rotate carry right, then accumulator becomes this and the carry flag goes to 0. So it follows the command right. In this program we have demonstrated the jump not 0 command. So in the first line we have incremented a, because initially a is 0, so now a will be 1 and 0 flag will be 0. Now if we make jump node 0 L, so jump occurs to L 1011 because 0 flag is 0. So now the program moves to L, which is this line. Then we move a this, then we out a, and then we hold. Here we can see that the middle three lines do not occur, which is move a 0 0 0 1 1 0 0. In the simulation we can see this happens. Here we have incremented a, so a is now 1, 0 0 flag is 0. Now if we implement jump node 0 L command, the program moves to L and stores in a 1 0 1 0 1 0 1 0. We can see that here that this happens here, and then the output a occurs and the program halts. Here we have to notice that the middle three lines does not occur. Here another thing is to notice that when the jump node 0 L command occurs, then the program counter changes accordingly. Like here the program counter starts with 0, then 2, then 4, then after that when the jump command occurs, it suddenly jumps to 1011, as here in the code L is equal to 1011. After the jump occurs, the program moves normally, like here. After 1011, the program counter increases by 2 and goes to 1101, then 1111. In this program, we have shown that, when the jump node 0 command does not occur. So if we move in A all once, then we increment A. So now A becomes 0, so 0 flag will be 1. So jump node 0 L command will not occur and the program will move to the following line, which is move a 0 0 0 0 1 1 1 1, and the program will halt. Now we can see that this happens. In the accumulator we can see that firstly all ones are stored in the accumulator, and then when we increment its value, it becomes all 0 and the 0 flag goes up. So now the jump node 0 command will not occur and the program moves serially. So now the move a 0 0 0 0 1 1 1 1, this happens. Here we can see that this occurred. In the accumulator we can see that 0 0 0 0 1 1 1 1 is stored, and then the program halts. Here the last two lines of the program does not occur. Here you can also see that the program counter moves serially, which is 0 0 0 0, then 2, then 4, then 6, then 8, like it moves serially. In this program we have demonstrated the push and pop statements. So here first we have moved 1 into A, then we exchange BA, B has the value of A. Now if we push B, so now B equal to 1 is stored in the stack. Now if we move 2 in A and exchange BA, so B has now value of 2. Now if we pop B, so it again restores the value of B is equal to 1 from the stack, and then the program stops. So here we can see this here. Firstly, we load 1 into B register, and we push this value to stack. Here the stack address increments 1, and in this address of the stack the value of B is stored. So in this stack address 0001, the value of B, which is also 1, is stored. Then we load 2 into B, which is shown here. Then we again pop B. So the previous value of 1 will be stored in the B register, which we can see here. We can also see that the stack pointer has also decremented by 1. It means that it has moved to a previous value. In this program, we will see the call and return statements. First, we move 1 into A. Then we call the address, which is 1101. Here, the program counter will move to this value, which is 1101. Then we move A2. Then the next one is return. Here, the return statement will move the program to the next statement after call address, which is the third line. Move A3. Then the program stops. In the simulation, we can see that firstly we move 1 into accumulator. Then we call address 1101. So if we look at the program counter, we can see that firstly it is in 2, then it is 4, then suddenly it jumps to 1101. It indicates that the call address has happened. After the call statement, we do move A2. Here we can see that 2 has moved into accumulator, and then we do the return statement. So after the return statement, the program will move after the call statement, which is 0100. Here we can see 0100. Then we move A3. Here we can see that A has value of 3, and then the program halts. Here another thing to notice that when the call statement occurs, the next address of the program is stored in the stack, which we can see here. The next line after the call address is 0100. Here we can see that when call occurs, the 0100 is stored in the stack in the address 001, which we can see here. When the return statement is done, then this value is again popped into the program counter, which we can see here. The value 0100 is again popped in the program counter here, and the stack pointer again went back to 0. In this program, we demonstrate the function of OR and XOR operations. This is very simple. We first move byte into A, then we OR A address 1. This ORs the value at address 1 with the accumulator and stores the result in accumulator. This is done in the bitwise fashion. So the result is this, and when we do XOR, the result is this, and this matches the simulation results. Thank you.